Hello there, everyone. If you can see, today is day 28. What we're going to be doing is we're actually starting your brand new unit, and your new unit is thermodynamics. Now, thermodynamics in physics is the study of heat and temperature. So first, before we even start anything, we got to define those terms and make sure that you are comfortable with the type of terminology. So, our agenda for the day, what we are going to do is we're first going to start out by just asking ourselves, how in the world do we represent thermodynamics first in science and in physics? How do we represent heat and temperature? And then we are going to ask ourselves the question, what happens to an element whenever you add heat? And heat is a very specific definition that you're going to learn in a second. Now, homework wise, a big part of thermodynamics is knowing what temperature means and getting you all away from that stupid Fahrenheit scale because 32 to 212 is ridiculous. No. So, what we are going to do is that due at the end of the week, that's going to be April 30th, of just end of Friday next week, you have 4 practice problems on temperature. Of one's converting Fahrenheit, Celsius, Kelvin, all of the good, and it's in the quizzes section of your Canvas page. So you can knock that out pretty quickly. But let's go ahead and get started. Let's just first talk about what we're going to be doing today. Is that first off, you're going to be able to figure out what heat is, what temperature is, and how they're described. You're going to be able to describe the change of heat inside of a system, and a system is just you know, a functionality of elements and trying to figure out how many elements there are in that specific thing that could change temperature. And then finally, as I said, you need to be comfortable converting from Fahrenheit, Celsius, and then the SI unit is Kelvin. So let's first talk a little bit about your unit. Your unit is a really actually not that long. Of what you are going to do is that first off today is just temperature and heat, getting you started, trying to figure out what temperature is and what heat is. Of After this, we're going to go into heat exchanges, what happens with heat whenever it's exchanged between objects, and then something very specific is called specific heat capacity, and that determines how much heat an object is willing to give off at a certain amount of time. Then we are going to talk about calorimetry. This calorimetry, what it is it's really to get you prepared for chemistry, because calorimetry you do a lot in chem, so this is your baby step into it. And then finally, we're going to talk about phase changes and heating curves of what happens to elements after they gain a certain amount of heat or go past a certain temperature. So let's first start out with your definitions, because think I've said heat and temperature already like 5, 6 times. But number one, temperature. Temperature, what you need to know of is it's the measurement of the average kinetic energy of the particles in a substance. That specifically, temperature changes whenever energy is added or removed. Of Temperature is, again, just a measurement. It's talking about exactly what the measurement is between two specific states of an element. So it's a measurement of the average kinetic energy, okay? Then you have to know immediately that temperature is proportional to the kinetic energy of the atoms, and it's directly proportional to the kinetic energy in atoms. More specifically, that the more kinetic energy, the higher temperature. The less kinetic energy, the lower the temperature. So if you have a very low temperature, your atoms are going to be moving slowly, and if you have a very high temperature, then your atoms are going to be quicker and quicker. Let me show this to you in a different way. So I'm going to flip on over. What I have is that you can see I have just a simulation here. And what I am going to do is I am going to pump in a gas of just a light species. Now, right now our temperature is at 300 Kelvin. I want you first to notice what ends up happening if I remove heat. And you have to think to yourself, well, our temperature is dropping. It's now 80 something Kelvin. Keep on going, keep on going, keep on going. And you notice as we get colder and colder and colder that our atoms, our element, is actually starting to slow down. The temperature drops. They're going to start being really sluggish. And you notice that there's not a lot, happening. And eventually, I don't actually know if we can get to 0. But even at 1 Kelvin, you can tell these atoms are not going to be moving very quickly. Oh, we did get to 0 Kelvin. Oh, but they don't represent 0 Kelvin correctly. I'll teach you why in a second. Now, let's go the opposite direction. Instead of removing heat and changing the temperature to be lower, we're going to add heat. And as I am adding heat, it's slowly going to build. And I just want you to think, as I'm stalling for time here, the temperature is going to rise. If the temperature rises inside of this box, what's going to happen to the kinetic energy of those atoms then? Remember that temperature is just a measurement of the average kinetic energy, and kinetic energy is just the energy of moving items. You've learned this before. We've done kinetic energy before. So, as I'm increasing the temperature, you see that my kinetic energy is also increasing. The speed of my atoms, the velocity of those atoms is increasing directly with the temperature, meaning that as the temperature gets higher and higher, then the velocity of my atoms also increases. And even now, you can see I'm at 1,000 Kelvin and it keeps on going, keeps on going. They're traveling faster. My pressure is building because now I'm in an inside box, and all of this, again, keep on going until eventually at 6,000, 8,000 Kelvin, the pressure becomes too much and it's just going to blow off the lid because those atoms have so much energy. That's the main idea with you trying to figure out what exactly the temperature has in relationship to the atoms. So, again, less temperature, slower atoms. More temperature, faster atoms. Okay. Now, let's talk about heat. Heat is that specific type of energy. That heat by itself tells you the amount of energy. Heat and temperature are not the same thing in physics. They really are not. Temperature, again, is a measurement. Heat is the specific amount of energy that is traded between items of different temperature. Now, heat we can't denote by a little lowercase h, capital H. Heat is actually denoted by a lowercase q in physics, and we'll get into types of equations later, but not today. So, a lowercase q is heat, and again, heat is just temperature. Now, energy can transfer in two specific ways, either that something's going to gain energy or something is going to lose energy. If you are losing energy specifically from an item to its surroundings, we call that an exothermic reaction. The system becomes colder and the heat exchange is negative. Again, think about direction. It's going away. It's negative. If you gain energy, then it's called endothermic, and that heat is absorbed from its surroundings and the system becomes warmer. And then your Q is positive. These are the only two ways in which energy can transfer. If you lose it, it's exo. If you gain it, it's endo. Now, there is a way in which this always travels, but in order to figure it out, I want you to do it at-home experiment. And yes, actually go and do an at-home experiment. So you're going to have some fun. I don't know, go and call some of your younger siblings in order to go and be, test subjects. Don't mind. But actually do this experiment. It takes about 30 seconds and it works out really well. So here's what I want you to do is that at your at-home experiment, I want you to grab just a bowl of ice water. Now, I mean put at least enough ice in where it makes I don't know, like a mix of it. You want a lot of ice and a lot of water. The idea here is that you want to drop that temperature, and to add in addition with it, I want you to add salt to this bowl of ice water, or this mug, whatever in the world you have. Salt actually goes and lowers the amount of energy that's ice can contain. It goes and it drops its freezing temperature, so it's going to make it even colder. Here's what I want you to do is I want you to get a bowl of ice water and to add salt. And then the other thing, and let's change colors just to be a little bit extra, is that I want you to do this obviously in a kitchen, somewhere in a faucet. I want you to turn a faucet of water as high as it goes, as hot as it goes. Now, of course, do not get it to scalding temperature where you're going to injure yourself. As warm as possible. But your body is very prone to responding to changes in temperature very quickly. It's very good at it, and this is such a fun and easy experiment to do. So you're going to do this two ways, and I'll be nice, and I'll actually change color once more. And what do we? Let's go Nerinx green. So here's the first one. What I want you to do is I want you first to go in the cold and literally stick your hand into that bowl of salt and ice and water, and I want you to then hold it for 30 seconds. And I want you to count out 30 seconds. Again, this is going to be one of those times that you're like, oh, it's 30 seconds. But after you actually start counting, yeah, it's going to hurt. It's going to be freezing and your hand's going to turn a bright red because of it. It's losing energy. It's exothermic. So you go and you pull or put your hand into this ice water for 30 seconds. Then afterwards, what you do is that immediately after those 30 seconds, I want you then to go and to hold it under that faucet for another 30 seconds. Make it something where it's not going to injure you, of course, and if you feel pain, then obviously take your hand out. But you're going to notice a reaction because it's either going to feel really, really good or it's going to feel really, really bad. And I want you to first think of what ends up happening. So hold it under the, like just in that bowl of ice water for 30 seconds. Really get your hand acclimated to that temperature and then switch it from the cold to the hot. Then your second trial of this, you're going to reverse it. You start out with the faucet for about 30 seconds again. And then I want you to dip it into the cold water for 30 seconds. One of these two is going to feel a whole heck of a lot better than the other one. And what I want you to do is, again, go and do this experiment. It takes 5 minutes. Everyone has ice and water in their home, hopefully. And then you can figure this all out. Okay? So go do this now. All right? 5. Okay. So, if you actually did my experiment, you should go and you should figure out that there's a big conclusion here to be made. And what it is that heat always moves in an area of high concentration to low concentration. Basically, the heat lost always equals the heat gained. So, what your experiment is meant to teach you is that that transfer of energy, your body does not like transferring temperature that quickly. Whenever you go from first the cold, no, where's my cold? To the cold to the hot, you flip the direction, then immediately your body is like, oh, this feels amazing. I'm gaining energy. Your body wants to gain as much energy as possible. But whenever you go from the warm faucet and your temperature gets acclimated there to the freezing cold bowl of ice water, your body feels and reacts as pain. It feels absolutely awful because what you are doing is you're actually reversing this process. Your body is losing energy. Think of it this way: every single item across the board always wants to gain energy. Every single element, item, no matter what, always wants to have an endothermic reaction. So the temperature change and the transfer of energy is always going to be from an area of high to low concentration. It's always going to warm up. It will never, ever, ever just like cool down just by itself and be like, oh, no, it's always going to gain energy. That's what that at home experiment is supposed to tell you. Now, what we are going to do is that first off, we need to talk about temperature. This video, and I've learned unfortunately that I'm not able to play videos for you, but what this video is that this is the history behind the Fahrenheit temperature scale. You go and you probably ask me all the time, Mr. Tate, why in the world do we use Fahrenheit? Why is 32 or 212, or you'll see the math even for temperature is ridiculous. And it is. But if you want to know the history behind it, this is going to be the video. Now, I'm going to skip past this because you know my feelings already on the imperial system and we don't need to go over those again. But we are going to make one big, gigantic table of Fahrenheit, Celsius, and then the actual SI unit is Kelvin. And we're going to write the temperature in which water freezes for each scale, in which water boils for each scale, the absolute zero for each, and then finally each one is going to have an equation. And we need to figure out how to solve for that specific equation. So let's first do it for Fahrenheit, and then I'll come back and I'll write each one. But let's first get a nice pretty pen color of, well, let's go back to magenta probably is the contrasting color here. So let's do that. So Fahrenheit. First one is that Fahrenheit by itself, its freezing temperature of water is 32, which is a ridiculous number. It's just random, basically. And then its boiling temperature is 212. Now, in order to convert from Celsius into Fahrenheit, you need to use this equation. It's that the temperature in Fahrenheit is equal to 9/5 multiplied by the temperature in Celsius plus 32.0. So let's go back to our chart and we'll say the temperature in water freezes in Fahrenheit is 32 degrees Fahrenheit. The temperature at which water boils in Fahrenheit is 212 degrees Fahrenheit. And then finally, our equation for temperature degrees Fahrenheit is equal to, and again, it's 9/5 times the temperature in degrees, so temperature degrees Celsius, and then you add on 32 in the end, plus 32.0. Okay. There's Fahrenheit. Let's go on to Celsius. Celsius is like the forefather. It's the actual temperature scale that you would assume that scientists use because it's a 0 to 100 scale. Now, something to notice about this equation, this is temperature Celsius. If you're trying to find temperature Celsius, it is 5/9 and then notice the parentheses. You have to do the temperature Fahrenheit minus 32 first and then plug it in. So let's go back to our table and we're going to write 0 degrees Celsius, 100 degrees Celsius, and then temperature in degrees Celsius equals 5/9, and then parentheses, the temperature in degrees Fahrenheit minus 32. Okay. And then finally, let's talk about the actual SI unit. The SI unit is Kelvin. Now, notice I am not saying degrees Kelvin. Degree means measurement. Again, Kelvin is not a measurement, so we do not put degrees. The freezing temperature of Kelvin is 273 Kelvin of water. The boiling temperature of water is 373 Kelvin. Immediately, that's 100 Kelvin difference. You should be thinking then, Kelvin's based off the Celsius scale. It's not the Fahrenheit scale. And then we have absolute zero, which is 0 Kelvin. And we'll get a little bit more into that in a second. Now, to convert from Celsius to Kelvin, you just add 273 Kelvin onto it. So, if we want to start out, again, the temperature in which water freezes on the Kelvin scale, come on, pen, is 273, and again, not degrees, Kelvin. The boiling is 373 Kelvin. Absolute zero is 0 Kelvin, and then your temperature in Kelvin is equal to temperature in degrees Celsius plus 273. That's the main idea. Now, this chart right here in front of us is like your saving grace. This is everything that you need to know about temperature scales in physics ever. That's why I'm saying, like, if you're wanting to actually draw something and take some notes for today, draw this. It makes it so much easier. Now, let's talk about absolute zero again, because absolute zero is 0 Kelvin. So, absolute zero is actually the coldest temperature possible. Like, period. That's it. It's done. Since temperature is a measurement of the average kinetic energy at 0 Kelvin, there is no kinetic energy. If there is no kinetic energy, then immediately particle motion would completely stop. Your particles would not move. And it's based off the temperature and volume of a gas. Now, here's a fun fact is that, well, I'll start out with two. Number one, the coldest place on the entire universe that we know of is here on Earth because we have always, and using some really, really cool technology, we can get close, like marginally close to absolute zero. But obviously, we have never hit absolute zero. And I say obviously because you're like, Mr. Tate, why can't talk? By itself, you know time as like an atomic clock. An atomic clock is like cesium atoms that go and they vibrate, and all of a sudden, those number of vibrations is what we represent as time. If the particle is not moving, then that means that those vibrations have stopped. If you and your body represent time as the amount of times in which the particle vibrates in a specific, like, sequence, but it's not moving, then absolute zero literally stops time. How cool is that? So, by itself, immediately, no, we've never reached absolute zero. And more than likely, we never will reach absolute zero. Even if it's 0.000 100 zeros 1 Kelvin, you're not at absolute zero yet, and time is still going to progress, just very, very slowly. That's the main idea here. So, first, let's just try one problem by ourselves, and after we do our problem, then we'll call it a day. So, our problem is that today's low temperature is 47 degrees Fahrenheit, and the high is 286 Kelvin. I want to express both the high and the low temperatures in terms of degrees Celsius. So let's do this together. What I like to do anytime I do these types of problems, and especially if they're like broken up like this, let's just do it this way. Temperature high equals, and temperature low equals. If I want to change both into just degrees Celsius, let's first start out with what we got. Of the low temperature here is 47 degrees Fahrenheit, and my temperature high is 286 Kelvin. Now, if we want to get both into degrees Celsius, let's go back at our table and try and figure out exactly what we need. If I'm just going to start with that temperature Fahrenheit. To get into temperature Celsius, I need to take 5/9 multiplied by the parentheses of that temperature Fahrenheit minus 32. So let's go on back and let's do that. Of temperature low. Again, if I want temperature Celsius, then temperature degrees Celsius is going to be 5/9 multiplied by the parentheses of that temperature degrees Fahrenheit. So I'm going to say 47 degrees Fahrenheit minus 32.0. So I'm going to have 5/9 multiplied by 47 minus 32, 15. And then you go and you plug it in. So immediately my calculator, where's my, oh, I left it over here. All right, my calculator, I go and I say 5/9, it's 0.555 repeating times 15, and I get 8.3 degrees Celsius. Now you ask yourself, Mr. Tate, how many sig figs? And I'm going to ask you, how many did you start with? Start out with 2, end with 2. 8.3 degrees Celsius. 3. Oh, that's not a point. That's degrees. So 8.3 degrees Celsius is my temperature of low. Now let's do the temperature of high. Again, to get the temperature in Kelvin, if I write my equation, temperature of Kelvin is equal to my temperature in degrees Celsius plus 273. So if I want temperature in degrees Celsius off of temperature degrees Kelvin, I'm just going to do temperature in Kelvin minus 273 equals my temperature in degrees Celsius. So just plug it in. 286 Kelvin minus 273 equals, I have 286 minus 273, that should be 13, 3 sig figs, 13.0 degrees Celsius. Fine. That would be my high temperature, and then this one would be my low. That's the change of the day. So that's the end of heat and temperature. As I said, you got 4 questions just posted just for practice. for you on your Canvas page. You can use this one as an example for it, and I will see everyone next time. Thank you. Stay safe, everyone.